Take the number 1260. On its own, it looks like nothing special, a plain 4-digit number you might see on a receipt. But watch what happens when you pull it apart. It factors as 21 times 60. Now look only at the digits. 1260 is made of a 1, a 2, a 6, and a 0. And its two factors, 21 and 60, are made of a 2, a 1, a 6, and a 0. The exact same 4 digits, just rearranged. Nothing added, nothing dropped. The number has been rebuilt out of its own digits, split cleanly into 2 pieces that multiply back to give it. Try that with a random 4-digit number and it almost never works. Take 2013. It does split neatly into 2 2-digit pieces, 33 times 61. But the digits of those pieces are a 3, a 6, and a 1. And 2013 is made of a 2, a 0, a 1, and a 3. They do not match. The vast majority of numbers, when you break them in half, hand you back digits that have nothing to do with the ones you started with. 1260 is one of the rare ones where they line up perfectly. That is not a fluke of 1260. There is a whole family of numbers that do exactly this, factor into 2 halves, that between them use up every one of the original digits. They have a name, and this video is about the rule that defines them, the handful of small ones, and how you would ever go looking for more. Let us make that idea precise, because the precision is the whole point. Start with a number that has an even count of digits. 1260 has 4. Split that count in half. 4 digits means each half is 2 digits long. Now you are looking for 2 whole numbers, each exactly 2 digits, that multiply to give your number. For 1260, those are 21 and 60, and each one is indeed a 2-digit number. Those 2 factors have a name. They are called the fangs. And the condition is this: the digits of the 2 fangs, poured together into one pile, must be exactly the digits of the original number. Same digits, same number of each, nothing left over on either side. When that holds, the number is called a vampire number, and the 2 factors that build it are its fangs. There is one more small rule to keep things honest, which we will get to, but this is the core of it. An even number of digits, 2 equal-length fangs, and together the fangs carry exactly the digits of the number, no more and no less. 1260 is the smallest number in the world that passes this test. The equal-length part is doing more work than it looks, so let us dwell on it. Every composite number factors into 2 pieces in lots of ways. 1260 is also 4 times 315, and 2 times 630, and 36 times 35. Only some of those splits have any chance of being fangs, because the fangs are required to be the same length, each exactly half the digits of the whole. So a 4-digit vampire must be 2 digits times 2 digits. That immediately throws out a factor like 4, or like 630, because one piece is too short and the other too long. You are only allowed to look at splits right down the middle. For 1260, 36 times 35 is 2 digits by 2 digits, so it passes the length test, but its digits are a 3, a 6, a 3, a 5, which are not the digits of 1260. It fails the digit test instead. 2 separate hurdles then. The 2 factors must each be exactly half the length, and their combined digits must rebuild the original exactly. 21 times 60 is the only split of 1260 that clears both. That is what makes it, and every number like it, genuinely rare. Once the rule is fixed, an obvious question is how many 4-digit numbers pass it, and the answer is small enough to just list. There are exactly 7. 1260, which we have met, is 21 times 60. 1395 is 15 times 93. 1435 is 35 times 41. 1530 is 30 times 51. 1827 is 21 times 87. 2187 is 27 times 81. A nice one where the fangs are near mirror images. And 6880 is 80 times 86. That is the complete list. 7 4-digit vampire numbers and not one more. 7 out of the 9,000 4-digit numbers there are. So this is not a common property that most numbers happen to have. It is a tight little club, and every member had to earn its place by passing both tests exactly. Now for the small, honest rule we set aside earlier, because without it, the whole idea falls apart. Consider the number 126,000. It factors as 210 times 600. Both of those are 3-digit numbers, and 126,000 has 6 digits, so the lengths line up 3 by 3. And the digits match too. 210 and 600 together give a 2, a 1, and 4 zeros, which are exactly the digits of 126,000. By the rules so far, that would count, but it feels like a swindle, and it is. All we did was take 1260, or rather its fang pattern, and staple zeros onto both factors. Multiply any fang pair by 10 and 10, and the product gains 2 zeros, and so do the digits, for free. You could manufacture endless fake vampires that way, and they would all be hollow, just a smaller one wearing extra zeros. So the rule closes the loophole with one clause. The two fangs are not allowed to both end in a 0. At least one of them must not be a multiple of 10. 210 and 600 both end in 0, so 126,000 is thrown out. But notice 1530 from our list of 7 survives, because it is 30 times 51, and 51 does not end in a 0. Only one fang is a multiple of 10, which is perfectly allowed. The rule bites only the true cheats. Here is a twist that makes the family stranger. A vampire number can sometimes be built in more than one way. Everything so far had a single pair of fangs, but once you climb to 6-digit numbers, you find ones that split into valid fangs 2 different ways, using the same 6 digits in 2 distinct arrangements. The cleanest example is 125,460. It is 204 times 615. Check the digits, 2, 0, 4, 6, 1, 5, which are exactly the digits of 125,460, so it is a vampire. But it is also 246 times 510. Different fangs entirely, and yet those digits are 2, 4, 6, 5, 1, 0, the same 6 digits again. One number, 2 completely separate pairs of fangs, both legitimate. And this is genuinely uncommon. Among the 148 vampire numbers with 6 digits, this is the only one that can be bitten 2 separate ways. Every other 6-digit vampire has just one pair of fangs. So 125,460 is, in a small way, the most vampiric 6-digit number there is. Step back and ask how the population grows as the numbers get longer. With 4 digits, there are 7 vampires. With 6 digits, there are 148. With 8 digits, the count jumps to 3,228. So the raw number of them keeps climbing, and fast, roughly 20-fold at each step here. But climbing counts hide how sparse they really are. There are 9,000 4-digit numbers and only 7 vampires among them, so fewer than 1 in 1,000. There are 900,000 6-digit numbers and 148 vampires, which is fewer than 2 in 10,000. Even though more vampires exist as you go up, they make up a smaller and smaller slice of all numbers. The family grows, but the pond it swims in grows much faster. So vampire numbers are not vanishing, but they are thinning out, rare and getting rarer as a fraction, no matter how many of them there turn out to be. That rarity raises a practical problem. If you wanted to find every vampire of some length, how would you actually do it? The naive way is to march through the numbers one by one. For each number, list all its factorizations. Keep only the ones that split right down the middle, and check the digits. That works, but it wastes enormous effort because the overwhelming majority of numbers are not vampires, and you find that out only after grinding through all their factor pairs. The better way is to turn the search inside out. Do not start from the numbers, start from the fangs. Take every possible pair of 2-digit fangs, multiply each pair, and simply check whether the product uses the same digits as the 2 fangs you multiplied. You are generating candidates from the fang side, where the digit condition is easy to test, instead of hunting for fangs from the number side. That single change makes the whole thing tractable. Instead of testing every number and factoring it, you sweep over fang pairs, which are far fewer, and each check is just sorting a handful of digits. It is the same trick that turns many search problems from hopeless to easy. Build your candidates from the structure you are looking for, rather than searching blindly and testing everything. So step back and the whole picture is simple and a little charming. A vampire number is one you can split into two equal-length fangs, whose digits, taken together, are exactly the digits of the number, with the single caveat that the fangs cannot both end in 0. 1260 is the smallest, at 21 times 60. There are exactly 7 with 4 digits, 148 with 6, and thousands more beyond, growing in count yet thinning as a fraction of all numbers. None of this solves anything or unlocks a deeper theorem. It is not that kind of fact. It is a small, exact, self-referential quirk of how our base 10 numerals happen to combine. The sort of thing that is true forever and simply was not noticed until someone thought to look. 1260, quietly built from its own 4 digits, and 7 of its kind hiding among the 4-digit numbers, is enough.